Well, welcome to the Sunshine Coast Astronomy Club. We're going to be going. We have two presentations tonight, one with Simran Nerval, and then we'll have one with Bruce on Sky of the Month. Just a couple cleanup things here. During Simran's presentation, she said she's indicated there's be three parts. So after each part, she'll allow questions on, she'll ask for questions vocally. Otherwise, keep yourself muted. You can send questions to the moderator through the chat, and then that way Charles will send to Simran at the end of the meeting. Also at the end of the meeting, instead of just shutting down, if a few members are interested, we'll have an open forum socializing. Okay, so if everybody's set, I just want to bring up that Simran Nerval is a master's student at Queen's University and a researcher with the McDonald Institute studying theoretical cosmology. She studies gravitational wave production during the expansion of the early universe. Before coming to Queen's, she did her undergraduate degree at the University of Toronto in physics and astronomy. While she was there, she was part of the LiteBIRD collaboration and worked with the Canadian Space Agency to figure out how well the LiteBIRD satellite would be able to determine what occupied during the earliest moments of the universe. Alongside her research, she spends time doing a variety of science outreach for events ranging from organizing virtual classroom visits for Let's Talk Science to running a virtual national symposium on astrophysics for high school students. So with that, I would like to turn this over to Simran and hear what she has to say.
Well, thank you. 1 second, and I'll share my screen. Okay. So yeah, actually, just quickly before the actual presentation starts, I'll just say a word or two about the symposium, because the first day is actually open to anybody for all ages now. So if you'd like to join, it's a free event. So feel free to use the link to join, and then you can hear talks from leading scientists on dark matter, dark energy, and galaxy evolution, and then as well as a panel on university. But yeah, the second day is still just for high school students, and they'll be doing a coding workshop where they get to use real data to make their own rotation curves. But yeah, so just a quick plug about that. But now I'll go to my talk, which is Spacetime Fluctuations from the Early Universe. And I'm going to start with the takeaway. Don't be afraid if you don't understand necessarily what it means. I'm hoping by the end of the talk, you'll be able to understand the takeaway. And that is that gravitational waves can be used to understand the earliest moments of the universe. And why is this even important? Well, if we can understand how the universe started, we can then understand why and how the universe formed the way that it did. So I'll go over what a lot of cosmologists do at the beginning of talks is this brief history of the universe, where as you go in this direction, you're going through time. The size of the cone represents how large the universe is at that time. So we have the beginning here, which was the Big Bang. Then this period of really, really fast expansion known as inflation, which will be one of the main topics of my talk. Then at a microsecond, or at 0.000001 seconds, protons start to form. Then at about 0.01 seconds, you start having nuclear fusion. So hydrogen starts to form, so just a proton and an electron. And then this nuclear fusion continues until about 3 minutes. Then as you fast forward to when the universe is about 300,000 years old, you have the cosmic microwave background, which will also be one of the main things that I'll talk about tonight. And then nothing really happens until the universe is about 100 million years old, when the first stars and galaxies started to form. And then as you go forward to today, you have when the universe is as old as this, so about 13.8 billion years old. So now I'll tell you a little bit about this cosmic microwave background and why we can't actually see before this time period. So imagine you were at a party and it was really busy and you wanted to be able to go to the other side of the room. Well, this is going to be really difficult. You're probably going to hit off of a bunch of these people, and it's going to take a really long time for you to be able to get to the other side, even if you even can. But then as the night starts to die down and people start to go home, it might look something more like this, where it's going to be really easy for you to get to the other side of the room. You're probably not going to hit into a single person while you're trying to do that. Well, this is just like the photons are the light particles in the early universe. You bouncing off of people while walking in the party is just like these light particles bouncing off of the matter particles in the universe as they're trying to free stream. So that looks something like this. There was this period where there's lots of these electrons and neutrons and protons, and these light particles or photons kept bouncing off of them and couldn't free stream towards us until a certain point where the protons and electrons and neutrons started combining into atoms. And then there was enough room for the photons or the light particles to free stream towards us. And we could take a picture of the universe at this time period, and that's known as the cosmic microwave background. And this cosmic microwave background, or CMB, was actually discovered by accident by two engineers at Bell Labs, Arno Penzias and Robert Wilson. They had this radiometer and they were trying to do different experiments with the galaxy and also satellite communication experiments. But they had this extra signal that they couldn't explain. And for a really long time, they thought it was just pigeon poop inside of this horn. But then they were able to rule that out. And they also were able to rule out that the signal couldn't be from the galaxy because they were seeing it in all directions, not just in one location, like where the disk of the Milky Way would be. And they thought, okay, well, there's this other signal from outside the galaxy, but it's probably not that important. And they were just going to write it as the small note in one of their publications. But then they were talking to one of their colleagues, and they said that they should talk to this other scientist, Jim Peebles. He was about to release a paper on his prediction of the cosmic microwave background. And whilst talking to him, they realized that that's actually what they were detecting. And this discovery was so significant, they actually won the 1978 Nobel Prize in Physics for it. Jim Peebles also won a Nobel Prize in Physics back in 2019, not only for the prediction of the cosmic microwave background, but also for a lot of theoretical work in cosmology in general. And one cool thing is that anybody on the call today that has ever used an analog television has also detected the cosmic microwave background. As you're flipping through channels and it's all staticky and fuzzy, about 1% of that static is actually the TV antenna picking up the cosmic microwave background. So scientists have tried to detect the cosmic microwave background from all directions from the Earth. And I'm going to show you what that looks like. But to start, I'd like you to consider the Earth. We know the Earth is a sphere. It's three-dimensional. But it'd be really difficult to, every time we want to figure something out about the Earth, like go to a globe. It'd be really inconvenient to just always have globes around. So we can project it down to 2 dimensions to make a map. So like a piece of paper or the computer screen. So here we have a map of the Earth. So even though it's 3 dimensions, we have it down to 2 dimensions. But we're going to be collecting data of the cosmic microwave background from all different locations on Earth, which means we're going to get a sphere of this data. And then we can make something like a map of the cosmic microwave background. So projecting the sphere of data down to 2 dimensions. And it looks something like this. So this is actual data of the cosmic microwave background from the COBE mission. And one thing to notice is everything's the same temperature and there really isn't any structure. It's all at about negative 270.4 degrees Celsius. And it's actually so much the same temperature, it's the same temperature up to 5 decimal places. And this is really weird. And I'm going to try to motivate why. Imagine you were having a dinner party and you invited 2 people over. And both of those people showed up with potato salad. Well, this is kind of weird. They had hundreds of dishes to choose from, but you can probably just dismiss it as a coincidence. But now imagine you invited 1,000 people over and every single one of them brought potato salad. Well, you can't really dismiss this as a coincidence anymore. They must have all talked before the party and decided to play this hilarious prank where they all brought potato salad. Not only did they all bring potato salad, they all brought the exact same amount. So 1.000001 kilograms of potato salad. Well, yeah, this is really weird, and it's just like the photons of the early universe. They must have all been in contact or talked to each other to be the same temperature at the cosmic microwave background. But if you recall, I said the cosmic microwave background happened when the universe was about 300,000 years old. But that means the largest volume that these photons could have traveled in that amount of time is approximately 1 million light years across, where a light year is how far light can travel in 1 year. But that actually only corresponds to a degree patch on the sky. So anything above these degree patches shouldn't be the same temperature as each other, but it is. And that's one of the biggest motivations for inflation. And during inflation, the universe expanded so fast that instead of these patches only being a degree on the sky, it actually expanded such that the whole cosmic microwave background would have been in contact with each other 300,000 years prior. And yeah, but before inflation, the universe was really, really small. So you have to take into consideration not just our normal physics, but also physics of the small scales, or quantum mechanics. Basically, quantum mechanics says that anything can't be perfect. So there must be these tiny changes. But we actually detect this in the cosmic microwave background. When you take away that average temperature, you're left with these really, really tiny temperature fluctuations or temperature changes on the order of microcelsius, or 0.000001 degrees Celsius. And this is actual data from the Planck collaboration. Well, you might be thinking, these are really small changes, like, do they even really matter? But there's actually a lot of information we can get from this. Even though with our eyes, we probably can't see any patterns that are happening, we can use computers to figure out how likely it is that different parts of this map are the same temperature. So basically what you can do is you can get your computer to draw a line on the cosmic microwave background. And then it can try to figure out how likely it is that this point and this point are the same temperature as each other. Then you can move the line and do it again. Figure out how likely it is that the ends are the same temperature. Move the line, do that again until you've gone across the entire map. Then you can go to a smaller line size and figure out how likely it is that the ends are the same temperature. And you can get it to move it and then figure out how likely those points are and do it again. You can go to even smaller line sizes and continue to do this until you've checked every line size and gone across the entire map to figure out how likely it is that these endpoints are the same temperature as each other. And then you can plot that in something known as the power spectrum. And there's a lot going on here, so don't worry, I'm going to go through it piece by piece. So we have this y-axis is showing us the changes in temperature and how likely it is that these two dots on these lines are the same temperature. On this x-axis, we have our line size, where the larger line sizes are here, and it gets smaller as you go further this direction. And then you have these little panels on the top, which are just showing you what the cosmic microwave background would look like at these different scales. And then here you have this wiggly line, and this wiggly line is the actual data of how likely it is that these different line sizes are the same temperature. And then this straight line here is showing us what it would look like if the temperature distribution was truly uniform. So if there was no patterns in how these different, where the different temperatures are laid on the cosmic microwave background. So here we have a 90-degree separation. So if you're checking right above you and then right out to the side and checking the sky, here it's about a degree separation. And then here is about 0.25 degree separation. So you might be thinking, okay, great, we can detect all this stuff from the cosmic microwave background, but you said that we can't look before the cosmic microwave background. But inflation happened before the cosmic microwave background. So how can we figure out anything to do with inflation? Well, scientists thought of a pretty cool way, and that's using gravitational waves. Recall back in 2015, LIGO, or the Laser Interferometer Gravitational Wave Observatory, detected two black holes merging. You can kind of see what that looks like by this artist rendition on the screen. We have these two masses, and they're orbiting each other. And as they're doing that, they're causing these ripples in the fabric of space and time itself to go out. And these ripples are known as gravitational waves. And this discovery was so amazing that they actually won the 2017 Nobel Prize in Physics for it. But we know space isn't just this little fabric. Space is three-dimensional. So instead of considering this fabric and what it looks like, we can consider it like a 3D grid of space, where we have this mass moving around in this lattice of space. And you can see as it's moving, it's pulling and squeezing this fabric of space as it's moving around. but we actually live in like a 4D space-time. So we don't just have these 3 dimensions of space, we also have time. And here you can see this mass in the center. You can see how it's distorting space, but also at each point on this lattice, you can see a little clock showing you how time is affected by these masses. So you can tell how closer you are to the mass, the slower the clocks are moving, and the farther you are out, the faster the clocks are moving. Well, during inflation, when the universe is expanding and pulling space and time apart, it can cause these distortions, which cause gravitational waves. And then also you can have different interactions right after inflation that causes these different distortions as well, that will cause these gravitational waves to be emitted. And unlike the photons or light particles, gravitational waves don't care how busy your party is. It's kind of like the music of the party. Even if it's as busy as here or as empty as here, the music can still go through the room. It doesn't care how busy the party actually is. So now that I've told you a bit about inflation and motivating it and how we try to detect them with gravitational waves, I will go into 2 different detection techniques. But before I do that, I was wondering if there was any questions from anybody on this topic before we move on to how to actually try to detect them.
Simran, Bill Haskett asks, what is the reliability of the temperature data? Given the differences are so small between individual points, wouldn't there be sensing error that would be comparatively large?
Yeah, okay. The data itself is very reliable because these experiments go on for years and years. Planck, I believe, ran for, I think it's like 8 years. Like, I have it in my notes in case somebody asked how long it ran for. 1 second. Okay, it ran for 4 years. So over time, you can collect enough of the data to be very confident in what the actual values are. Also, we have a lot of different experiments that are trying to detect them that all have slightly different systematics, so slightly different things that would cause noise from their experiment. And once they try to correct for those, and they spend years before the experiment flies to try to figure out how much noise the experiment itself will be producing to try to take that out. And all these different experiments agree on what they're seeing, independent of their individual systematics. So we can be fairly confident in what we're seeing here.
I have a question, Simran.
Yeah.
So it's still unclear to me how inflation smooths out the universe. I mean, wouldn't you have like, I mean, whether if the universe is really tiny at the beginning, then they're all really close. Okay, so they'd all be at the same temperature, and then whether it expanded slowly or rapidly, it's not clear to me that would make any difference on how smooth it was. It would be how close they were at the beginning. So can you explain that?
Yeah, sure. So I was trying to think of how to phrase this. So yeah, the universe is always like expanding, but as you can tell, at least from this plot, it's more of a moderate pace compared to here where it's really, really fast. So if the universe was just expanding at like a normal pace, given how long it was from the beginning of the universe until the cosmic microwave background, so about 300,000 years, if you just consider like a simple setup of like maybe it being like a sphere of where the photons or the light particles could travel, the distance across all of that is only like 1 million light years across. As far as they could possibly go without any extra boost from, which I'll explain that in a second. Sorry. As far as they could actually go just themselves traveling would be about 1 million light years across, but that only corresponds when we try to look at it today to about a degree patch on the sky, which is quite small. But during inflation, it's not breaking the fact that we know photons move at a very certain speed. They move at the speed of light and can't move faster or slower. But since the fabric of space and time itself was actually expanding, it allowed these photons to travel a lot further than if it wasn't expanding that fast. And it wasn't breaking any laws of physics because the photons themselves are moving at their speed of light, but the fabric of space and time was expanding itself. So the whole universe was expanding so fast and actually expanding so fast that it caused these photons to relatively move faster than like an actual photon could have moved on its own, because space was growing.
Okay, I'll have to give that some thought. Were there parts of the universe that were sort of still inaccessible to a photon, despite the fact that it was like okay, if the universe is rapidly expanding, then not obviously the okay, sort of what you're saying is that the photon can move much farther, but at the same time, the universe is getting larger much quicker, so it's still going to have a hard time getting there because the universe just got a lot bigger. You understand what I'm saying?
I think so. So I'll try to address at least what I think you're asking. So actually, first I'm going to clarify the question to make sure I'm understanding correctly. So
okay. So here's the question again,
okay.
because it was a bit I'm gathering that the problem is that the photons can't communicate across the large distances needed to sort of harmonize the temperature.
Yes.
So what they're saying is, okay, what happened was space expanded rapidly, which allowed the photons to move much farther and therefore kind of communicate with more distant parts and even out the temperature.
Yes.
The problem I have with that is, but space, because space was also expanding, it was putting the universe farther and farther apart as well.
Mm-hmm.
So the photon is no better off being able to travel fast, or communicate over larger and larger distances, because the universe is expanding fast, and so it's still getting away.
Okay. Yes. I see what you're saying. Yeah. So the photon, after space has expanded that far, it can't communicate to like the really far parts anymore. But the reason why they're the same temperature is because they were able to communicate before space expanded so fast. So they were all communicating before, they were all like the same temperature. Space itself expanded, so their density went down. There's less photons for like a unit area or unit volume. Yeah. But they were talking before, and the same amount of time has passed, so they are still the same temperature, even though they can't communicate anymore because space has expanded so fast.
Okay, thank you. That's very helpful. Thank you.
No problem. Was there any last questions before I move on to the next part? Okay, it doesn't seem like it, so I guess I'll go on. So I'm going to talk about two detection techniques for detecting these gravitational waves. The first one will be how to detect gravitational waves in the cosmic microwave background. And then the other one is to try to directly detect these gravitational waves. So the first one, as I said, is detecting the cosmic microwave background. But in order to do that, first, I would like you to consider just a simple wave moving through a slinky. So you can see as this wave is moving through the slinky, it's causing these parts of the slinky to move up and down. So just consider one ring of the slinky and what the wave would be doing. It would look something like this. This should be working. One sec. Cool. It would, if you have this like ring of particles or photons or really anything, it would cause the ring to move up and down. But if you have a gravitational wave, instead of it moving up and down like this, it actually would look something like this, where this gravitational wave is coming out of the screen. So it's causing this ring of particles to get squished in one direction and like squeezed out in the other. And this keeps happening over and over. So imagine that these were just photons or light particles in the early universe. They're being like moved around a lot in all these different directions from the gravitational waves. Well, I told you that these photons or light particles have a temperature associated with them, but what I haven't told you is that they also have these electric and magnetic fields. So here there's this little diagram where there's a photon moving out like this, and you have the magnetic fields and these electric fields that are 90 degrees apart, so they're perpendicular to each other. And then another way to visualize this is to look at this GIF there's a lot going on here. So maybe just try to focus like on one of the arrows and see how it's moving as this photon is moving across here. So the photon is moving and you have these electric and magnetic fields moving with it, where the only thing we've said is that they have to be perpendicular from each other or 90 degrees apart. But we didn't say they had to be facing up like this. They could be in any direction as long as these two fields are 90 degrees apart from each other. And this direction that they're oriented is called the polarization. So imagine you had just like a light source, so like the sun. It's going to emit light at a bunch of different polarizations, so like any direction possible, really. But then you have something known as a polarizer, or in this case, like a vertical picket fence, where there's these vertical holes. It's only going to let the light go through that is vertically polarized, and it's going to block everything else. Well, if this light interacts with anything, like for example, if you have the sun and this unpolarized light, so light in a bunch of different directions, gets reflected off of some water. And then you're wearing some polarized sunglasses, which is kind of like two vertical picket fences. It's only going to let the vertically polarized light get through the picket fences and block all of the horizontally polarized light, which is good because the horizontally polarized light is actually glare, and that's hard on your eyes. But anyways, yeah, so these picket fences only let the vertically polarized light in. And so this water is kind of like, if you consider if light can scatter off things like in the universe. So you have light from the Big Bang, so the sun. It's unpolarized, it's going in all these different directions, and then it can scatter off of electrons in the universe. Then it'll travel towards us, and we have our detector, which is kind of like a pair of polarized sunglasses with one horizontally placed picket fence and one vertical picket fence. So we can measure how much horizontally polarized light there is and how much vertical polarized light there is. Well, you might be thinking, okay, great, electrons can scatter light, but we were talking about gravitational waves. Well, just like how these electrons can scatter light, gravitational waves can also polarize the light. Because if you remember the circle of like the light particles or the photons and how they're getting stretched and squeezed, it can move them around and change the direction of their electric and magnetic fields. So we have light from the Big Bang. It's going to become partially polarized from gravitational waves. And then we can try to measure this polarization in the cosmic microwave background in our detectors. So the polarization that we can try to measure from the cosmic microwave background are known as E modes, and where this is just showing you it in one dimension. So you have up and down or horizontal, and B modes, which are off by 45 degrees. But you might be thinking, well, the cosmic microwave background isn't one dimension. We measure it like a map, so in 2D. In 2 dimensions, it's not this simple, but it kind of looks like these cartoons here. Where on this side, we have the B modes. So you have these curled polarization patterns. And on this side, we have the E modes, where it doesn't curl at all, and it just is like diverging out. And what this looks like in a cosmic microwave background map is something like this. Where here, we have our E mode polarization. So you have all these divergent patterns. And here you have our B mode polarization. So you have all these curled patterns. And yeah, and one thing you might be thinking is, well, you said when you measure the cosmic microwave background, you're measuring temperature. Well, the temperature is just the intensity of the light. We can slightly change our detectors to not only detect the intensity, but to detect how much of the E mode polarization there is and the B mode polarization as well. And if you recall, the power spectrum, where this is the temperature power spectrum, so how likely it is that each of these dots are the same temperature as each other, we can do the same thing and figure out how likely it is that each of these dots are polarized the same. And we can make the other power spectra of the cosmic microwave background, where here is that temperature one. Here is our E mode polarization. Here is our B mode polarization, where this dark line is the E modes being gravitationally lensed into the B modes. And here in this light one would be like these inflationary B modes. And as you can see, because this is actual data from different experiments, these error bars, or how uncertain we are in these measurements, are really large here. So we only really know how high the gravitational waves could be, but we don't 100% know exactly where this sits. And that's what people are trying to figure out what the amplitude of the spectrum actually is. And a lot of people are trying to do this. Here's some of the experiments, definitely not all, but some of the notable experiments, where we had WMAP, which was a satellite in space, Planck, which was a satellite in space, Polar Bear, which was a telescope in Chile, BICEP, which was a telescope in the South Pole. Currently, we have experiments like the South Pole Telescope, which is a telescope in the South Pole, CLASS, which is a telescope in Chile. And then for future experiments, there's things like the Simons Observatory, which will be in Chile as well, and should be running hopefully soon, like in like a year or two. Then other experiments like LiteBIRD, for example, which is an experiment that I've worked on and will be working on again. And then other satellites such as PICO. So before I move on to talking about directly detecting gravitational waves, were there any questions about how we can try to detect them through this cosmic microwave background polarization?
Well, Simran, Bill asked, hang on. Are the phases of the magnetic and electrical waves in sync like in the illustration that you showed?
Sorry, I'm just gonna, like this? Yes, they are.
Anybody else have a question? Okay.
Okay, if not, I can go to the last portion of the talk then. And that is, instead of trying to detect these gravitational wave signals and how they affect the light particles or the photons, it's actually just trying to directly detect these gravitational waves. And this time, instead of going with this at the end, I'll start first with some experiments that are looking for it. So I'd already talked a little bit about LIGO, so the Laser Interferometer Gravitational Wave Observatory. And it has 2 locations, in Washington State and in Louisiana. Going forward, there's going to be experiments such as LISA, or the Laser Interferometer Space Antenna, which is actually this constellation or triangle shape of 3 satellites that will try to detect these gravitational waves. Here's a little GIF to show you kind of how it's going to orbit. So here we have this yellow dot, which is the sun. And then we have this blue dot, which is orbiting the sun, which is the Earth. And then this triangle is showing you how LISA will be orbiting along with the Earth around the sun. So to explain how these interferometer gravitational wave observatories work, I'm going to explain how LIGO works, since it's a simpler geometry with just that L shape. So here is showing you that L of like how LIGO is set up. And what's happening is it's emitting this laser light. And as it emits this laser light, it'll go into this thing here, which will split the light. And the light will travel down the length of both of the arms, will bounce off of the reflectors at the end and come back. And then it'll recombine. And it recombines in such a way that the light cancels out and there's no signal here. But as a gravitational wave starts to go through this detector, it'll cause the arms to stretch and squeeze, which causes this light to no longer cancel out, and it causes this flashing signal. And when we can detect this flashing signal, that's actually us detecting the gravitational waves. If you recall in that the GIF of the circle of the particles where they were being stretched and then squeezed in the other direction and kept going like this, since this is perpendicular, it's 90 degrees apart, it's an L, one arm will be being stretched while the other one's being squeezed, which is why we're getting this flashing, because they're being stretched and squeezed differently. You also might be thinking, well, what if there's an earthquake or something? And then that's what's causing this flashing to happen because the arms are moving. Well, that's why there's 2 locations. There's a location in Washington State, then there's a location in Louisiana. Then they know if they're detecting the signal at only one of the locations, it's not from a gravitational wave. They have to detect it from both of these locations. And once we can detect these gravitational waves, we can put it on a plot that kind of looks like this. But there's a lot going on here, so I'm going to go piece by piece. So theorists like myself can try to figure out, for different models of inflation, how much gravitational wave we expect. We put it on a plot that looks like this, where the y-axis is showing us how strong the gravitational waves are, where the higher we are here, the stronger they are, and the lower we are, the weaker the signal is. And then it's against the x-axis, which is the energy. So here it's lower energy, and here is higher energy. So here are some predictions that I've made using simulations of how much gravitational waves we expect from different models of inflation. We then can figure out, for experiments such as LIGO and LISA, how much gravitational waves they would be able to measure. where the shaded region here is the amount of gravitational waves and at the energies that these different experiments could have measured. We can also use astrophysical experiments such as the cosmic microwave background, galaxies, element abundances, and figure out how much gravitational waves they would be sensitive to. And that's what this shaded peach region is here. Well, you might notice that these predictions don't actually overlap with any of these shaded regions. And for these experiments to be able to detect these gravitational waves, they have to overlap. And this motivates the development of sensitivity in this regime, either from having more sensitive CMB galaxy experiments and such, where it will lower this bar. So it's getting quite close to at least these predictions, but also it can't tell us what the energy scale is, because you see this whole thing is shaded in. It's independent to the energy. But also people can try to make these gravitational wave detectors in this energy scale here. There have been a little bit of work done there, but there needs to be a lot more work to be able to make a detector that can actually see these gravitational waves from inflation. And yeah, so now just to go back to the takeaway. We know that gravitational waves could have been produced from these earliest moments of time or inflation. And we can use things like detecting the polarization of the cosmic microwave background, and then also this direct detection of these gravitational waves to figure out if we can see how much gravitational waves were actually produced by inflation, to then be able to figure out which model of inflation is correct, or if there's another theory we have to come up with for what actually happened in these earliest moments of time. And I can take any questions now on this section or any of the other sections. This went faster than I thought it would. So sorry about that, but now I have lots of time to answer questions.
So Simran, Bob's asking, why not have a third dimension in LIGO, a laser in the z-axis? Would this not give more accurate direction?
So like the L, but then like one coming up?
Yeah.
That would be very difficult to stabilize because of wind and lots of other things like that. The amounts that these that LIGO is changing, I guess I can go back to that video. The amount that these arms are changing is actually really, really small. It's sensitive to 1/10,000th the radius of a proton. So these changes are really, really small. So any sort of like jiggling in it would cause a lot of issues and would cause like false detections. So building something like vertically up off the Earth, it wouldn't be able to be as sensitive to those really, really tiny changes in length.
I have a question.
Went on to ask if you could go down, but I know I've been to LIGO. The arms are 4 kilometers long, so yeah, you'd have to drill down 4 kilometers, and I don't think that's practical.
Yeah, and like even things like Snow Lab, for example, which is underground, it's only 2 kilometers underground, which was already like a huge thing for them to be able to do. So 4 kilometers would be a lot.
So Simran, I have a question.
Yeah.
And that is on that axis, on one axis it had energy and on the other one it had strength.
Yes.
And I was a little bit puzzled by, what's the difference between strength and energy?
Oh, I see. Okay. So energy here would be like the energy of like the actual gravitational waves. So it's analogous to like the frequency, just with a friendlier name, because the frequency of a wave is you can get the energy from that wave as well. Just like, for example, with light, you have like different frequencies of light. You have like ultraviolet light and infrared light or optical light, and all of those different frequencies correspond to different energies of the light. It's exactly analogous with gravitational waves. You have those different frequencies of gravitational waves, and that can tell you the energy of the gravitational wave. This is, oh, sorry, yes.
So you're saying then that the gravitational, you're expecting gravitational waves from inflation to be higher in frequency than what LIGO can detect. Is that?
Yes. Yes.
Okay.
Well, there's lots of different, yes. So I'll say that, but like with an asterisk, and I'll explain the asterisks. So yes, for some models of inflation. So in particular here, I'm looking at at a certain type of models of inflation. that wouldn't be able to be detected very well in the cosmic microwave background, which is why we have to look at these direct detection techniques. For there to be a very large imprint in the cosmic microwave background, inflation would have had to happen at a very, very large energy scale and been basically very violent to have changed these, the polarization of the different like photons in the early universe. So we don't actually know exactly how much gravitational waves happened. And in the cosmic microwave background, we have an upper limit on how much gravitational waves there could be. But the cosmic microwave background can only detect so much. So yeah, so there's a bunch of different models. And since we haven't detected it yet, we haven't narrowed down which one we think it is. That's what people are trying to do. So this is a particular type of model. And here, yes, it can't be detected by these. The gravitational wave frequencies are higher than what these experiments can detect, because these experiments are mostly designed to be able to detect things like black holes merging or neutron stars merging. They weren't designed to be able to detect inflationary gravitational waves.
Okay, thank
Because
you.
it's a very new field detecting them, so that's what they were trying to go for first.
Okay, yeah.
So is the frequency of inflation gravitational waves higher or stronger?
For these models in particular, yes. So these signals are in the megahertz to gigahertz ranges, whereas which would be, so a megahertz would be like 10 to the 6 hertz, and a gigahertz would be 10 to the 9. Whereas
Yeah.
LIGO and LISA and such, they detect more like the millihertz to hertz ranges. So yeah, the frequencies are much higher for these particular models of inflation. And these models of inflation are actually pretty good models of inflation, because for the way the model is set up, you can make it mimic a lot of different other models of inflation and what they would see. You can also use this model and figure out how it would affect the cosmic microwave background as well. So that's why I chose these ones, because they're good as generic models of inflation. They can mimic what a lot of models do. But yes, in general, at least from what I found in my work, the frequencies are a lot higher than what these can detect.
So the left-hand side is the LIGO.
Yes.
Okay.
Yes.
So the LISA, the spacebound one, would be on the right-hand side here.
Okay, I will try to explain this again. I actually have a plot with the actual labels. I didn't have this one just because it looked a little, with all the legends, it was a bit much. But yes, so LISA is this green one. So it's actually in the millihertz range. LIGO is all of these lines. And this one is the red one's another future space satellite, but it's like really, really far in the future, which is why I didn't spend much time talking about it. But yeah, so Lisa's actually even further to the left here.
Simran, is Virgo on here as well? I understand.
Virgo would be considered in the LIGO ones.
Okay.
Yeah. Yeah. But yeah, I can go off of this one because it has the legend, and there's like, yeah, the legend can be a bit much for but yeah. Did I answer that question? Was there follow-up questions on that, or?
No.
Were there any other questions?
I like the legends.
Oh, okay.
Simran, some of us actually did go down to LIGO a few seasons ago for night lights. We went down to LIGO Hanford, and we were expecting just to go into maybe the control room and interview a couple of people. And he said, "Hey, we're doing maintenance. Let's go inside." So we were actually in the building and saw, how this laser system worked. It was pretty amazing.
That's really cool. Yeah, I've never been to LIGO. Since I do theory stuff, they just tell me this is what the experiments can detect, and then I just use that to compare to my simulation stuff.
And there was someone earlier saying, how do they detect things like earthquakes? They do. They actually were showing us there on their screen. This is the crows pecking at the top of the nitrogen tanks that cool the tunnel, and this is the traffic on highway, whatever, and they've got it all figured out. They just subtract it. It's
yeah. Yeah, it's a really amazing piece of like engineering to be able to figure all that out. A lot of work and a lot of people working on it.
Oh yeah, it's truly amazing. I mean, one of the things that this is something I never expected down in LIGO Livingston down in Louisiana. They have people shooting at it because they're upset because it blocks their old trail that they used to use to go hunting. So people have actually the two tunnels for LIGO at both locations have this structure over top which is bulletproof. That's why it's crazy.
Wow, that's really crazy.
You can't do that at Hanford because it's on the Hanford Nuclear Reservation, and you know there's only certain ways you can get in there, and security would be all over you if they didn't understand what you were up to there. But the one in Louisiana, yeah, it's crazy.
Yeah, that's really shocking. And like, not only is a bunch of people's like livelihoods, jobs, and time with that, that's also like a lot of money to then just be shooting at. That's pretty crazy.
It's well, there's some crazy people out there, I guess. But it's a pretty, if anybody here does get down to Richland, Washington, you can drive in there, and there are tours of the facility. I guess with the pandemic, that's kind of stalled at the moment, but you can actually go in and you won't be able to go inside. We were very lucky, but you'll be able to see the structure from the outside, and they have all kinds of displays to explain what's going on. And you can see the screen up there where you can see what they're actually doing. So yeah, it's cool.
Yeah, that does sound cool.
Yeah, I was there with Charles, and yeah, the mirrors that they reflect the laser beams from are just suspended from sort of tiers of pendulums that are with extremely fine wires and very heavy pendulums, and it's a very much a Rube Goldberg apparatus, just like it's quite comprehensible what they were doing. It's just that they've done it to an incredible degree. So it was quite interesting to see the mechanism. You can understand it. It's not just electronic wizardry. It's a physical gadget.
Yep, yeah. They have a model, right, a full size, test model there in the lobby that you can see, so you can understand how it works. The one weird thing was when you go in there, you have to wear laser safety glasses because it's an infrared laser. You can't see it. Mm-hmm. So if it ever got out, you could be injured and not even realize, you're walking into it. So we had all of these fancy, very expensive goggles on, which made everything look like it was blue in there. And you got so used to it after 2 hours, you just sort of assumed this is the way it looked until you started looking at pictures from your cell phone. You realize it doesn't look like that at all. It's just normal lighting, but it's because of these safety glasses that it looks quite different. It was fun.
Yeah, that sounds really cool.
Any other questions?
Can you put up the graph with the legends on it again?
Yeah. Did you want me to go through it at all, or?
No, that's good. I just took a screenshot of it. So it makes it a little easier for me to understand.
Okay, sure. Yeah.
So these ones here on the lower right, that's just a model right now then. There's no data to support that, or?
Yeah, so with inflation, we don't have any, we only have upper bounds on how much gravitational waves there could be from both this direct detection and from this cosmic microwave background. Yeah, we have, detecting these gravitational waves would be like a direct measurement of what happened during inflation. So we don't have any of these direct measurements. We have more just like indirect things, like how uniform space is, how flat space is, how there isn't a bunch of things like monopoles and stuff all over. So we have a lot of this like inferred evidence, but not this direct evidence. If we could detect something like this, it would be the direct evidence of it. So yeah, we're still looking for that. That's That's one of the big questions that still exists in I guess the universe, and also like in cosmology.
Mhm.
Simran, I'm just curious, what got you into this? Like, why?
Yeah.
How did you get here?
So I've always been really, really into science and like physics and like, well, I used to think and math, but then you learn what like theoretical math is when you go to university, and it's like, oh my goodness, no, I just liked using math for science. That was not what I really liked anymore. But yeah, so growing up, I just always really loved it. And then when I was in like early middle school, so like 6th grade, I realized that because I was torn between going into science and being a classical musician, and I decided, you know what, no, that's a hobby. So I decided to go full force into science back then. And then when it came to inflation in particular, during my undergrad, so I did physics and astronomy, I really liked my courses, but all the cosmology courses I found like the most interesting, because I've always had all the questions of like, how did the universe get this way? How did it start? Why is it expanding? What's it even expanding into? Like all these different questions. And in the cosmology classes, people like we're trying to tackle those actual problems, which is really cool. And then I was lucky enough that I did my undergraduate thesis with Professor Renee Flotchek at the University of Toronto. And I got to work on stuff that actually had to do with this inflation, which was really cool because it was trying to understand the very earliest moments. And if you can understand the earliest moments, you understand why things happened like since then. So I always found that really, really fascinating. And I also really like to be able to look at like all this theory side. So things like figuring out these curves, but then also trying to connect that to observations, because if you have a bunch of data and you don't know theories, you can't do anything with it. And the same way, if you just have a bunch of theories and there's nothing to compare it to, it's really not that useful. So I really liked this combination, which is why I like to make, well, I guess plots like this, or what I did with LiteBIRD was try to figure out how well it can constrain inflationary models, even though it's not built yet. So just trying to run simulations on what the data could look like and doing things like that. Yeah, so that's kind of how I got here. I'm actually going back to the University of Toronto in the fall to do my PhD, more with the LiteBIRD side of things, and a bit with this. Yeah. So still inflation though. But yeah.
I have a question. Hi, Simran. That was an amazing talk. Thank you so much.
Thank you.
A silly question, but I mean, I know there's lots of different models of inflation and you can get some fairly exotic things. Do you have a personal favorite model of inflation and why?
Yes. So there definitely are a lot of models, and some that are very, some can be very out there and some can't. I don't know. I personally really like, so the E and T models actually stem from the same base model, which is the alpha attractors. And with those, it's not like a super fine-tuned model, which is great, which means you don't have to, have very, very specific things for it to be able to work. But also just changing the parameter values in your model, you can make it duplicate a lot of different observables. So what it would look like in the CMB, or what it would look like in the direct detection, which is really, really useful, which means that you actually could get this huge wide variety of what could happen just from these models. So it's not like a very specific case where it could only look a certain way. And I really like that, because then you don't need to have this like super constrained things to happen to be able to get these results. So in particular, I really like these ones. But yeah.
Awesome. Thank you.
No problem. Were there any other questions from anybody else?
Could you tell us everything about everything?
Thanks,
I don't really think I have enough time for that.
Sorry, I know it's a big question, but I kind of like to know everything about everything, if I could.
Yeah, that's the dream. People to know as much as possible.
Clarify that for me, that's all.
Sounds like she's working on doing just that.
Very interesting. Hey, I sent you a chat if I could record it, and I guess these are all get posted on YouTube because I got in late, unfortunately.
For those of you who joined later, we are recording tonight's presentation. I will edit it in the morning and it will be on the YouTube channel.
Thank you so much, Charles. That's great.